Hi, this is Codeweaver. Welcome back to Codeweaver Plays Games. I think my audio is already set up here, and I'm going straight back into Exapunks because I was having a lot of fun with it last night, and I already actually, after the stream, came up with a solution to the problem that I was stuck on, and I'm just going to continue on from here because, why not strike while the iron's hot? That's how I feel. The only gotcha is that I have food being delivered not too long from now, and when that happens and rings, I am going to have to go claim that. But until that happens, when that happens, I'll just pause the game. But until that happens, let's go straight on into Exapunks. So here we go. I'm going to show you. What happened when I ran my program, because I actually came up with two solutions. One of which was quite obviously in the vein of what they intended, and another one which was ridiculous and they wouldn't even rank it, but it still worked. So I'll show you both. So let's quickly go and read over the text log over here, since that's something I don't think I can replay except for scrolling back, and I don't want to lose track. So. Starting here, I've been exploring the phone system in my local area, and I found some anomalies. There's one number that just beeps when you dial it. A lot of numbers do that. It's a really weird beep, though. Oh, it could be some sort of government beep. Sure, government beep. You know what I mean. Alright, so, having solved this one, I'll do the outro after I show you the solution. So, here we go. We're going to go into here, and I'm actually not going to show you this one. I'm going to show you the one that actually worked the way it was intended. Now, there's probably a couple of different varieties of this, but the basic idea here is that you basically send a wave of sort of self-replicating drones down into the channels, down into these channels, until they get to the end, and then they grab the file. They kill off the bot that's there because the bot's holding onto the file. They kill off the bot, and then they drag the item back. So what I have here is I have two bots, one of which stays at home and acts as a home base marker. That way I don't have to keep track of how far back I have to go, because they're both, as you can see, in local mode. And local mode for communications between bots says only talk to the bots that are actually in your local space. So what this does is XA just sits there and tries to send a message to XB that says, "Hi, I'm here. This is where you should be." But B isn't going to actually listen to that until he comes back. He's going to go out, and there's going to be a whole bunch of bots that sort of spawn down into the channels. And then when the file gets grabbed, they walk back through the channels and through the -1 links all the way back home, basically up to the root where XA is. When they get to XA, they know that they've gotten to the root because they can basically ask to see whether or not there's a message pending. Now, this is one of the rare differences between file access and register access and all that kind of stuff, and network communication. For network communication, you can query to say, is there a message pending, and if I ask for it, can I get it without blocking, basically stalling? No other communications mechanism has this. So what that means is that if you want to be able to ask the question, does a result exist? If so, I can grab it, or if not, I can just go on with my life. Only happens with bot communication. So I take advantage of that, right? Because as I walk back up the chain towards the root, from wherever the file is, I can ask, is a message pending for me? And because it's only local, the only time I'll ever get a true coming out of that test is when I'm all the way back in the main room, at which point I can then choose to receive the message, unlock A so that it dies, and then drop the file where I happen to be. That'll be XB. So XB comes back and says, yeah, okay, I finally made it back. You can rest now, and then I can drop the file and rest myself. That's what XB is going to do. Now, the only thing that made it tricky is that when I'm walking down the levels in order to be able to get to the file, basically every time I go down a level, like I go, say, that first step, I now have two branches, and then each one of those has two branches and so on. So I can obviously clone a pair each time I go in, or at least I'll clone myself once, and then each of us can go down a different branch, and then each of those will clone themselves once, but then there'll be 2 of them in each branch, and each of them will go down each of the 4 branches, and so on. I can't do that once I get to the very last one. If there's a file person there, or if there's another bot there, or if there's a file stored there, because there's only 2 slots and one of them's eaten up by the file. Attempting to replicate myself in that case will stall the program. And that's no good, because that's exactly the point at which I want to be able to grab the file and go. But the gotcha is that if you try to grab the file and it's not there, your bot immediately dies. So I'd love to be able to say query to see whether the file exists, and if it doesn't, then try to do some other cloning activity, like leaving, going down to another level. Actually, I don't have to go down to another level at that point. But if I try to grab the file and it doesn't exist, then the bot just dies. And if I want to make this a really simple program, what I want to do is I want to keep, as I arrive at a node, I'd like to be able to ask, is there a file here? Even if it's the first one, I know, just for simplicity, I know that the minute I step into this first node, if I ask, is there a file here? I'd like for it to say no, and then I'll say, okay, well then I'll just keep going deeper. And then I'd like it to say yes when I finally reach the end, so that I know that I've gotten to the end. So my solution to this is basically, I'd like to be able to ask the question and get a no back, and then just walk deeper until at least one of the bots says yes right at the end. For all the other bots that reach the tail end here, if they were to ask that question, does a file exist here? If I could get an answer back without killing the bot, then all I would do is then try to walk further, and that would destroy the bot. But I don't want it to die just because I asked the question, does a file exist here? Unfortunately, I have no choice, because I can't ask that question. All I can do is try to grab the file, and if the file doesn't exist, the bot dies. That's a problem, or the exa. I call it a bot, but the exa dies. That's kind of a problem, because it means that if I keep querying all the way down, none of my bots will ever get past the first stage. So, there's probably several different ways to get around this. My chosen mechanism was that every time I step into a region, the first thing I do is I send a sort of a pilot fish bot down into the next stage in order to ask the question about the file. And I only send I'm going to keep walking down, I'm only going to send myself and any clones that involve walking further and further down the tree after that bot has occurred. Now what that means is I'm spawning a bot who is only going to live if they actually grab a file in the next cell. That's going to fail everywhere except for the very last spot. But that bot, that pilot fish bot that goes into this last cell, is going to it's going to try to grab the file. It's going to not die, and at that point, it can basically start walking its way back. All right. Now, I don't have any clever communication really between the bots. I expect all of the bots that are intending on walking into the nodes deeper and deeper to eventually get to the bottom and then try to walk off, and they will self-terminate because of that. The pilot fish clones that I send ahead of the walking bots only go one step, but they will live or die based on whether or not they can grab a file there. So all of those will also die everywhere they try to do it, except for this one on the right. Or wherever it happens to be, because each one of them starts it up in a different location. And the only way this works is if the pilot bot goes there and checks first. Because once I get into that, once I send a bot into that spot, the one thing it can't do is clone any more bots to do any more work. All the cloning has to be done in one of the earlier stages, because as you can see, the number of available working spaces gets smaller and smaller. In all of these, I can do cloning. I can't do cloning in here until that file is picked up and removed, right? Another thing that makes this work is that if you try to link to a place but there's no room, the bot that tries to do the linking will stall there. So if I send a pilot fish into here, and then the bots that remain behind waiting try to then send walker bots down in, either themselves or a clone, the walker bots will stall in this location. But since there's only one file, even if these are already filled up with clones, one of them as a walker bot is going to walk down here, freeing up a spot. This guy is going to be able to walk back out, freeing up the spot. Sorry, not this guy, but the guy who goes and picks up the file will be able to pick up the file and walk out, which will clean up a spot here, at which point this becomes the same as all of these. Any remaining walker bots here will be able to get down into here, and then all of these will effectively behave the same, and the guy that grabs the file will be able to maneuver back because there's going to be enough space all the way up. So the primary thing that makes this work is that I send a swarm down, but ahead of the front line of that swarm are pilot fish that specifically go and query to see if a file exists. And if it doesn't, they die. The pilot fish die. And if they do, the pilot fish backs out as fast as possible so that it doesn't interfere with that advancing wave of swarm. That's the intent. So let's walk through this step by step to see how this works. So we step in, we send a pilot fish to the left and to the right. All right, and in the meantime, one of the pilot fish leapt forward because that's what it does. All right, this guy's gonna die. He's a pilot fish bot. This guy's gonna die because he's not gonna find a file. Or he will in a second anyway. That's the other pilot fish, and he's gonna die for the same reason. Where is this guy's actual code execution? He's going to try to grab 276. Oh yeah, so one of the things a pilot fish has to do once it launches is to try to kill a bot that's in the same room, because the one that actually succeeds is going to have to wipe out this bot before it grabs a file. So he tried to do a kill, didn't manage to do anything. This guy tried to do a kill, didn't manage to do anything. Now they're going to try to grab the file that doesn't exist, and these two guys are going to go. In the meantime, this guy is not a pilot fish. This guy is actually part of that advancing wave of walker bots. So XB0 and XB1 should be going away. This guy's going to go away, I think, this tick. File ID isn't found. It'll actually go away next tick because it takes a tick for it to go away. So that's fine. Then we're going to step. So this guy's a walker bot, and this guy, the original. So this guy's a walker bot, that advancing frontline wave of clones. So this guy went left. This original one didn't have anything better to do, so he's the one who's going to go right. So he sent a sibling, if you like, a sibling walker bot down the other way. So then we hit advance, and XB0 and the other guy over here, they died outright. Now we're starting to get clones. Sorry, now we're starting to get new pilot fish to go and check the file existence ahead. And the walker bots are going to stay behind and clone siblings to help do the walking that's going to follow behind. It's a little hard to see this because all these bots are stepping on top of one another. But just to be clear, we have two kinds of bots that exist, and I can't relabel them on the screen to make that easier to follow. But there's basically an advancing wave of walker bots that will eventually walk off the end of this grid. Walk off the ends of these nodes. When it gets to here, it'll try to walk off and it's going to die. That advancing wave has preceding it, like advancing ahead of even that wave, those pilot fish that go in and test to see whether or not it can grab a file. So let's see what happens when we get far enough through all of this cloning, advancing, trying to kill, trying to grab files. Here we go. This is a pilot fish trying to grab a file that came in from this node. I think that's a pilot fish as well, I'm willing to bet. Yes, it's in the pilot fish section, but it's gonna try to do a grab and it's just gonna fail. This guy and this guy are the two sibling walker bots that are gonna go in here. Now this walker bot is never gonna be able to get in here. It's gonna try, but it's gonna block trying to get in there. Because this guy is actually gonna start doing some real work. He's gonna, first of all, he's gonna kill off the bot. Is he about to kill off the bot? No, he did a kill, but now he's going to do a grab. This guy. Oh, that's this guy up here, XB7. Sorry. This guy's the one who just did a kill, and he's going to try to do a grab. In the meantime, this one is stuck. Where's this one? This one is XB7. No, sorry, this guy. XB is actually the original. Ironically enough, in this particular test. in this original, he's trying to do the link, but he's stalled. He cannot get in there because there's too much stuff going on. But that's okay, because in a minute, this guy's going to grab this and leave, and then this guy's going to keep trying to walk, and he's going to die just like all of his siblings. He just happens to be stalled because I'm doing other work with that pilot fish bot that is in advance of the walker bots. So, we are going to do a step. We've grabbed it, and the act of grabbing it freed up a spot, and that's exactly when the walker bot was able to get in. Now, we don't care about any of the grabber bots or any of the walker bots, because they're all going to try to advance one more space, and they're just going to die. So, we're going to step, and you can see that he's now walking his way back. And there's a number of bots that are attempting to be cloned and falling off into space. So we're going to, they're going to be trying to clone pilot fish bots that are going to try to advance. Now, the thing about the pilot fish bots is not only will they die if they try to grab a file and fail, but they'll even die if they walk off the grid in an attempt to get to the file and fail. So that works out for us just as well as the walker bots. So at this level, the pilot fish and the walker bots both die, not because of any file access, but because they can't go to the place to do any work. They just try to do a link and they just die. So all these guys are going to die, and that's fine because that's good cleanup. This guy is now completely free and clear. Now you can see that this guy is executing a loop where, let me see if I can do this. Gotta watch out for that food coming in. Sorry, this guy here is XB7, right? This guy's in this section where what he's doing is he's testing to see if a message is available. And if we fail to find one, then we're just going to loop back up here, and we're going to keep following these -1 links. Link -1, link -1, link -1, until that test is true. This guy has been sitting back here trying to send a message all this time. So he's our sentinel, if you like. He is our, because it's a programming concept. You put sentinel values in places where you want to be able to test when you get to them. That's what this guy is. He's a sentinel in a messaging sense. So, we're going to keep stepping. And all these guys are going to end up dying because all the clones, the pilot fish and the walker clones, are all going to try to step off and can't get anywhere, so they're literally all going to die. There's that. There's that. This guy's a step or two behind because this pair, this XB basically got stalled trying to get in here, if you recall, because of him occupying the space with the other bot and then the file. So then we do another step, then another step, and these guys are all now dead. So then we do another step in, but now this guy is going to do a test of MRD. This guy's still waiting to try to send the message because nobody's read it yet, but that test finally succeeds. We fall past the false jump and it succeeds. Now, in order to unlock XA and have it finally terminate, I need to read the message. So I'm going to read the message, but now he doesn't have any more instructions. And that's fine. That's equivalent to a halt for our purposes. We don't have to have an explicit halt. Then we drop the file, and then we have no more instructions, and then one more step, and we leave no trace. That's the completion. Now, every one of these operations is symmetric all the way down to the left and the right-hand channel. So you would expect this to behave the same way no matter which direction you go. You can also see, by the way, that whenever I spawn a new walker or I spawn a new pilot fish, they both have starting left and right variants in code. That means that I don't have to send a message to them to tell them which way to go. And I could have done it by way of sending messages, but instead I decided to go with unique entry points as the state management for startup, because I've discovered as a pattern. That I'm going to actually turn down the volume because I feel like I'm speaking over it, and it's lovely music. But anyway, as a pattern, when you start up a replicated bot, you have a couple of choices. You can start up at a unique location in the code, and that gives you a certain kind of state, because from that point on you can do a different code path or set your registers in a different way, or do something slightly different. And I actually use that to an effect here. I either at the very beginning I either start my first bot. I start my first bot going left because it just happens to be the first instruction. But from that point on, whenever I start out sending in my walkers at the tail end, I started out either left or right, and that means that the replicated one goes to the left on my screen. I realize it's sort of an upside down binary tree, but I called that left in this diagram. So what are you going to do? So I send a copy left, but I send myself right. So I only make as many bots as I strictly need to solve the problem. And that's why I have this advancing wave of walkers. And the unique entry points change sort of how I start up my behavior. But you notice from that point on, after left start and right start, we just do common code, right? Because at that point, once I've made my move, it doesn't matter. Everything should be the same at the next node, and the next node, and the next node. Same thing with the pilot fish. When I'm at a node and I want to send a pilot fish forward, I want to do it looking left and then looking right. I want to send one left and send one right. And so I replicate unique pilot fish to go and do that, but they have a unique entry point, left and right. Another way that you can control startup that seems to be a pretty good mechanism is you start up a bot and then you immediately send a message to that bot that gives them information on how to start. And that protocol of negotiation means that the startup bot can then go and do something. Now, I haven't been in a situation where I have more than one spawn bot capable of receiving messages that I send out, and that would change the care with which I send out messages, because I wouldn't want to start up two bots and then send them both the same initialization unless that's what I really meant. So, but in any case, I did not use a message sending scheme here. I used a startup point in the code. And so, because this makes the same decision at each node, it should be indifferent to how deep it goes. And because the left and the right cases only differ from the startup, I can keep this code fairly compact, right? And I should be able to find the message no matter where it is, because all this behavior is identical all the way down. Now, I will say that another possible approach to this, because I know the shape of the network ahead of time, is I could have a counter there that takes my bots initially as far as the bottom, and when I get to level, if I count this as 0, 1, 2, 3, 4, when I get to level 4, do special code, and that way I could race down there super fast, grab the file, and then race back with the one that manages to get there. That is, I could have state inside my bot which knows when it should look for a file. That could very conceivably create much shorter code. Basically, knowing the shape of what I have in front of me and exploiting that would make for a much more efficient robot, probably, because you could have a walk down really fast mode and then a just pick up the file if it happens to exist mode. I didn't write it that way. Proof is left as an exercise to the reader. I kind of want to go on to do puzzles. I like this because of its kind of recursive uniformity, and that just makes me smile. Because in principle, this could find a file anywhere in the tree, even if it wasn't at the end. No, they did not ask me to do that. Yes, I went overkill. But you know what? I do overkill. So I'm going to, first of all, because I'm going to show you my next solution, which is hilarious. But I can actually show you, as if I step through this, it does exactly the same operations, except that a different node finally gets the pilot fish. But from that point on, all the behavior is essentially the same as before, it's just in a different spot in the tree. And proof of concept, we can let this run all night, and we get a result. That's pretty cool, and I'm happy with that. That makes me feel happy. It's a small code base. It does maybe more work than it has to, but it's compact representation. I'm not too worried about this kind of stuff unless it indicates that there's something really terribly wrong with my program or I missed a trick. I do not know how Broach did this. That's really awesome. Probably something like what I described as my alternate implementation possibility. That's really cool, but I don't need to get on a leaderboard that badly. So continue editing. The reason why I find this cool is let's go to solution 2. This is freaking fantastic. Not because it's efficient, but because I actually managed to write it, and I'm feeling really, really good about this. So before I get into, you can see the code, but before I get into how this works in the code, the basic idea is, in principle, in any other kind of programming language, like in a modern programming language, or even in an assembler language where I have more facilities at my disposal, I suppose you could say, more memory, whatever. One thing that I could do, or the ability to query, that's another thing. The ability to query the existence of things, which is really, really hard in this. The only thing you can query about is the existence of messages. Everything else you have to try and die. which is like a hardcore limitation to work around. Let me tell you. So, what I wanted to do, what I would do in a normal programming language is do something like maybe like a breadth first search, or depth first search. Sorry, most likely a depth first search, in order traversal, and basically I'm going to go down what visually is the left hand side. Go all the way down, see if I can find a file. If I don't, go down this side, and then walk my way back up. And I'm basically going to visit every node in order until I find the one that I'm after. And when I find it, I'm going to drag it back. Now the problem is in order to do that, I have to have this guy walk all the way down and still survive to go all the way back up again, because I don't want to keep cloning walker bots. I want really there to be only one primary walker bot until the end. I made an exception there, but I only really wanted one primary walker bot that visited everywhere in the tree. But the problem is when I get down to here and I want to ask the question, is there a file? I have a problem. Because if I try to grab a file that doesn't exist, I just die. And that stops my ability to walk. So I can't do that. On the other hand, in all of these, I could replicate a bot to do that work for me. Except that if I'm already in this node, I can't do that without blocking the whole progress, because I can't clone a bot into a space I don't have. So it seems like I'm stuck. Well, the answer to that is right back to the pilot fish. As I walk down here, I basically send a pilot fish, again, in advance, to see if a file exists. And if it dies, which I can detect by trying to wait for a message a certain amount of time from it, then I know to just continue on my merry way walking. If it succeeds and I get a message back from it saying it succeeds, then I'm at my end state, because the one that went in there and did not die clearly grabbed the file. So the same logic for pilot fish exists in this as before, except that instead of walking back with it, instead of the pilot fish grabbing it and working its way back through while a whole bunch of things are dying at the tail end, I have almost no bots at the tail end created. But what I do have is I have this guy who's going to be walking and will survive the entire program, and I will have a pilot fish that gets sort of queried into the next cell to see if it can find that file. So in effect, I'm using, like with the other example, I'm using a pilot fish bot as a test case, because I can't test whether a file exists, but I can send a bot in there to try to grab it and then test to see whether or not that bot died. And I'm using the death of the pilot fish as a test to see what I should do for this guy. I should just probably show you how this works in practice rather than walk through all of the code. And let me say, this is not how I guarantee you they expect you to solve this, because it immediately pops up with a message at the tail end of this saying, this is not a small enough program to qualify for our leaderboards. But to their credit, they let you write the code, they let you run it and test for its acceptability as a solution, just not as a solution in the constraints that they wanted. Mad props to them letting me do that rather than setting a hard cap on the program size. So, I'm going to step through this a little bit, but I want you to keep in mind that because of this sort of uniformity of the behavior of this thing, I send out a pilot fish at every node and wait for its response, even if it's not at the tail, end. So again, this can be made more efficient by counting how deep I go and knowing that the last one is the one I want to do the pickup work. I wanted to make this as general as possible just to see whether or not it would let me. So this could find files that were anywhere in here. Another way, by the way, instead of sending a count, I could actually query the name of this thing, and I don't know what happens actually if you query a name when no name exists. Either an empty string? No, it would probably just die, so maybe that wouldn't work. Yeah. So, actually, there's another thing that this has to do differently. Not only do I send out a pilot fish to find the file, because I have to use death as a test case, I have to see whether or not I can go any further, because I don't want this guy to walk down here and then try to go deeper, because it'll just die. So not only do I have a pilot fish effectively for grabbing the file, I have a pilot fish to see if I can even walk forward. So that's pretty cool. Now the only consideration to shape that I make on this, or exploiting a structure, is that this is a complete tree. So I assume that when I get to a node, it has either both children or it has none. I could write this to be more complicated to avoid that constraint, but I have limits to my time. So this is pretty general as a behavior, as long as the tree is complete. Proof is left as an exercise to the student if you want to try to make it even more general than this. So, there is one other thing I should mention for those of you who know how depth first search or an in-order traversal works. I have to keep track of where I came from because although there is a parent link, I've got two problems. The primary problem so I have two problems. One is, when I walk back up, I want to know when I finally get to the root, because I don't have anybody staying behind to act as the sentinel in this case. So I need to be able to know how far deep I've gone and how far back I come. I also keep track of, as I go into a node, if I intend to go down the left-hand node, I want to keep track of the fact that I have to go down the right-hand node later. And so the way I did this was I decided that I would mark my ability to not go back from here as node -2, because that doesn't exist anywhere in the node scheme. And every time I enter a space, I mark that I need to go back, or I need to go down a different path, or go to the parent by way of leaving a breadcrumb trail. So the very first time I enter in here, you can see that one of the things that I do partway through this is I record that if I'm about to go down 800, I record that not only do I want to go down 801, but in the future I'm going to want to go back up 1. And I want to go down this one before this one. And so how would you do that in a programming language typically, or in a CPU that actually had this facility? You would use a stack. These are parameters. It's breadcrumb trails to know what to do when I come back out of a nested situation. And these are all effectively function calls. Every time I enter into one of these, I'm effectively evaluating this like it was a function call. And every time I step back out, I want to be able to unwind the stack and figure out where to go next. Now, it's not implemented exactly as function calls, as like pushing parameters for function calls and then popping them as I come back out. Not exactly. This is more what you might consider to be continuation passing style, where I don't push onto the stack the state that I am now. I'm pushing onto the stack sort of the future thing that I want to do, which is enough to solve this problem. I didn't have to get more elaborate than that, as it turns out. So I actually have a stack. But you could ask the question, where am I getting a stack from, right? Because these bots only have 2 registers, and one of them isn't even quite general purpose in the sense that it gets overwritten with truth values. X is general purpose. T is almost general purpose, except that it can have its value whacked by truth tests. I can't use F and M as general purpose registers at all, because they read and write from files and read and write from communications. There's no stack. There's not even any memory. I can't access any memory at all, except in files. So XA creates a file and uses that as memory, as random access memory, or in this case, kind of linearly accessed memory, because the stack basically grows as the file grows, and then as I clean up the file's tail elements, the stack unwinds. So there it is. That's how this is solved. I've implemented a depth-first search and in-order traversal, effectively, using a file as a stack and using 2 kinds of pilot fish to test if I can go deeper. Let's find out how this actually behaves in practice. Enough talking. So we create the file. That's our actual bot memory. I'd love to see a mechanism like this done by way of, instead of using an explicit file, maybe talking back to a bot back at home that manages memory for it. I don't know. There's all sorts of ways you could fake a stack. Maybe. We'll have to see. So there is our first pilot fish, and this is a pilot fish for trying to do the capturing of the file. I call it a capture probe in this sense instead of a pilot fish, but that's basically what it's doing. Go here, try to kill a bot, try to find a file, and if one doesn't exist, die. So now we know there's no file in there. So now we're going to clone our so what we're going to do is we're not going to clone left and right walkers. we're gonna create what's called a null probe to see if we can actually walk into that space. Now, if we can walk into that space, then we will. And if we don't, we know that we're at the tail where we can't go any further, right? So here we go. We send a message, which way to go. That, by the way, is one of the things. This one actually starts up with a message with the intent to receive a message, which tells it which way that this guy wants to test the existence of. Is that what I do? No. Is that? What do I do here? No, I actually send... I don't actually have to tell it which way to go, do I? Copy X into M. Oh, yes, because from here there could actually be left and right children. It turns out that that's not the case generally. Generally, you have two children. This is the one spot where left and right children don't both exist. But that's okay, because it's a special case for startup, and that's fine. But basically, we send this guy down here in order to see whether or not is actually walkable down here. Having tested that, F jump to null. So hang on a second. So hang on. Gotta follow my own code. This guy is basically the null probe goes down a path. Like, it receives a message on which direction to go. It goes down that path, and the only way to go in the first case is just into the first node. It walks down there and it tries to send a message, but it will not get past this link if it dies. So at this point, it's trying to send a message back to the primary, back to the guy who sent out the probe to test, the pilot fish for the existence of an ability to walk. So this is going to try to send a message. This guy back here is currently waiting. It is first tested to see whether or not the message existed, which you have to have a couple of no-ops in here to let it get down there and try to send the message. Otherwise, you'll get a false because it hasn't tried to send a message. So a couple of no-ops in here guarantees that this one manages to get to the point of sending a message if it survived. This fact that it got past this F-jump test says that it was false, that it failed the false test. So true, there is a message that exists, but when you test to see whether a message exists or not, you don't also read it. So I have to read it so that both of them agree that the message has been read. Now, having done that, the main bot continues to actually do its work. It now knows it's safe to walk there, and so it's actually going to walk there. This guy, on the other hand, has just received a message acknowledging that the primary bot has gotten the message, and it can just stop. It can just die, because we don't need him, and we don't want him cluttering up the path. So he goes away, and this guy is in the process of wanting eventually to link going down. Now, one of the things that I've got going on here, by the way, is that this guy's maintaining a file of where it needs to go at any given point. The place that he personally has not yet gone is 800, and that's what that seek is for. That seek basically bumps the file pointer from off the end onto this, because I'm about to erase it, because I'm about to go down into the first node. This, by the way, is eventually we're going to want to walk backward, and when we walk backward, we're going to know that we are at the end, because by the time we get back to here, we want to be able to know that we're back at the end so we can stop. So that's what that sentinel value is for. In any case, what this seek -1 is for is to be able to back up on the stack. That's popping on the stack. So the combination of seek -1 and void pops the value off the stack, which is what happened here. Then we go down the value that's currently still stored in X, which is 800. Okay, so that follows the link. Then we want to set ourselves up for, now that we're here, where will we want to go in the future? And because this is a stack, we want to pop these in reverse order. The place we want to visit first is 800, which is going to take us down this side. The next place, when we finish doing everything in that branch, when we get back to here, the thing that we're going to want to do is go down the 801 path. So that's what that's for, that 801. Right, which will take us down this side. But after that, when we come back here for the second time, where do we want to go? We want to go back up to the parent. right? So the -1 indicates we want to go back up to the parent, and the 800 means that we want to go left, and the 801 means that we want to go right. So we're going to set up on our stack, which is in the file, 1, 2, 3. Those are our 3 values in reverse order of how we want to visit. So that sets up our effectively our future. And then we do it right back up to the main loop. And the main loop basically keeps looking as to what to do based on this element right here, whatever it is that's on effectively the top of the stack, right? So once again, we're going to go and grab that value. So we just have a copy of it. We are going to see if it's -2 as a special case. No, it isn't. Is it -1 as I want to go up? No, it isn't. And at this point, we want to do what we did before. We want to go and see whether or not down the 800 path we can capture a file. And that's what the capture probe is for, right? So now the main code sits here waiting for a reaction message. So it's going to send, first of all, a go ahead and do your work message to the bot. And I could probably eliminate this maybe, but I kind of wanted it acknowledged that they were both more or less starting at the same time. I could get around that because acknowledging startup isn't something I necessarily need to do. I suppose the reason for this was as a debugging mechanism, so that if I couldn't do a clone, then I would stall the program and I'd notice that. But in any case, this is just a message being sent just for startup purposes. Now, having done that, this guy is going to do a couple of no-ops just to wait for the capture probe bot to be able to see whether or not it dies. But if it does not die, this guy is going to be able to send a message back in time. So let's see what happens here. We're going to go there, try to kill a bot, which doesn't do anything, try to grab a file, but we can't. File doesn't exist, so he dies. But what that means is back here, we're just at the point where we're going to test to see whether or not a message has been sent. This is false because it didn't. The capture probe bot did not manage. Oh, hello. I got a message saying this is about my food. Is it not? Yes. Sushi delivery here. Food left at the front desk. Isn't that delightful? All right. So I'm gonna finish this explanation and then I'm gonna go grab food. That is fantastic. Okay. And in any case, this test is going to fail because the bot that should have sent the message can't send the message. And because of that, we don't even have to read a message that doesn't exist. But it also means that that there's no file that's able to be captured there, right? So death is our test. Existence is our test, right? So now we're going to emit the null probe. So the capture probe was trying to capture a file. This is going to test to see whether or not we can even walk there. So we create the probe and we send an acknowledged message for starting, which is exactly what this other guy is going to be sending right here. So we do the acknowledge, which takes a couple of ticks. And then the null probe does a link, and right now the main probe is just waiting. It's doing no ops right now, waiting for us to possibly try to send a message. We try to send a message, and we block, but at this point we're just at the point where we can test the MRD. Now this sets it to true, which means we got an acknowledgement back, which means this guy lived. And so once again, we send a message back in time, not back in time. We send it back with sufficient time for the probe to get an acknowledgement. So this is copying out to memory that yes, I got here. This is and because the message is available, we do have to read it. We can't just leave it sitting around because we want both of these to advance forward in their code. And then this one can just die because we don't need him anymore. But this guy now knows. That it can move down because this guy got here and sent a message. Yes, it's safe. So there's our. Should have called that one the canary, right in the coal mine. Is it safe to go down here? So then we do this pair of operations, which pops a value from the stack, which is that 800 saying we're kind of done with this operation, right? We've done the work. And now I'm going to accelerate this a bit, but basically the same logic applies. Eventually, we're going to want to go back up here. We're going to want to do that last. What we're really going to want to do is go down 800 first, 801 next, and then 800, and then back to -1 at the last. So we have to push them onto the stack in reverse order, right? Sort of, again, continuation passing style. We're basically pushing on our futures. And so we push those on, and we just jump back to the main loop, and we're doing exactly what we did before. And we could do this indefinitely as long as we didn't run out of stack space, which is possible because the file can only be a certain size in this program. We can go as deep as you like, and we're going to, in fact, keep going as deep as we like. I'm just going to quickly accelerate this because I'm going to get to the last one. So we have not reached the tail end. We're going to send out the capture probe, which is going to go forward, and it's going to basically die because it couldn't capture a file. That's not really that surprising. We knew that was going to happen. But now we're going to try the null probe test, which is basically the can I even walk there in the first place? I do have to do it in this order, by the way, because when we get to here, if I did it in the reverse order, we'd get blocked. I'd leave that as an exercise for the student to find out why, but this is fine, because if the capture file probe can't walk, then it would die anyway, and not being able to get there is, for my purposes, the same as not being able to pick up a file. So it works out. So in any case, we're now going to send the null probe down. Now this is going to behave a little bit differently this time. We're gonna walk down into there. Actually, it's not going to behave any different because I'm actually going to go there. We're going to move down, and we're going to say we want to go into 801 and 800 if they... Now, there's a caveat here, if they exist. So what's going to happen is this. When we go back up to the top, we're still going to go through all of this, and we're going to try to send out the capture probe. The capture probe is going to try to do a walk, but it's actually going to die a little bit early because it's going to try to... They're going to send messages. It's going to try to do the walk, and it's going to immediately die. That's just as good a failure as not being able to pick up a file. So we're not really too worried about that, right? That's going to behave the same as it did before. But now we're going to try to emit a null probe. We're going to figure out where... We're going to tell it a message, where do we want you to go, to see if we can walk there. We do a couple of no ops just to wait for the result, right? But we know at this point, it tried to walk off the end and it failed. So actually, for the very first time, it's actually going to jump to null. Now at this point, we're going to say we couldn't walk down the 800 branch. That's what failing to get a message from the null probe tells us. We didn't get a message back in an expected amount of time. We can't walk there. So what do? Well, this pair of values again. We just pop a value off a stack, jump back to the main loop. We are literally done with the left-hand channel because we can't go down the 800 path. We can't go down the 800 path. So we just pop it off. We say, okay, we tried, but we can't go there. So then we do the same thing again. We try to do the test for capturing a probe down the right-hand side, which would be 801 if we could. We failed that, but we don't care. We then try to see, can we even walk there? And once again, it says we can't walk there. And actually, you know what? Now that I come to think of it, this actually shows that I could do it even if it wasn't a full tree, because I do test each of the individual nodes separately. Right? There's nothing wrong with that. So I actually made this more general than I thought I did. So, we then pop the value off the stack. The 801 branch is also not valuable. And then now, for the first time, we're back at the top of main loop, and we are going to test. We're not at the special case right at the root, but we are at the point at which the next thing that we want to do is actually the go back up value, right? That's what basically got read out there. And so we are definitely, for the very first time, going to say, well, now we're going to move up instead. Then we're going to link, and then we're going to pop that value off the stack because we're going back up. Then we go back to main loop. Now, what's the next path here? Well, the next path is actually 801. It's actually, we have not been down this side yet. So that is, in fact, the very next thing that we're going to do. And in fact, the same logic applies, that we're going to test. We're going to test, first of all, probe for files. Second of all, test for ability to walk. Then go there, and then try to test forward for the existence of a file, but that bot walks off into space, and so we get a negative confirmation. We then try to do the walking test, the null probe test, and that fails as well, and so we go back up, because the very next thing that we can possibly do, we actually tried the left-hand branch, the 800 branch from here, and now we do the same thing for the 801 branch from here, and that fails, and then at this point, the only place that we can go is back up, right? So this is not going to be terribly exciting for all of the rest of this, so I'm going to use one of the tricks that I discovered we can do, which is to set a breakpoint arbitrarily to future point and just run as fast as possible until we get there. And the point at which that's a thing is when the capture probe actually finds something, and that'll be only if this grab succeeds without dying. So if I think it's a control click on this. No, it's an alt click on this. That is not what I wanted to do. Cancel. Come on. Alt click on this. And so it zips down all of the locations until it gets to here. Now this is the point at which we sent in a capture probe and it finds a file. Now we go into a special mode. Now, I tried to figure out various ways in which I could have XA56, this guy, the capture probe, just hand off the file and send it back. Totally a viable thing, because in that case I would only need the one bot to do the remainder of the work. I went a slightly different direction. I made an exception about the multiple bots thing walking the tree just at this point, because I was kind of getting tired of this. And also the problem is XA56 at this point doesn't know how far back it has to walk. It has no knowledge. There's nothing tagging that final location as being a viable, that's the last spot, unless it sends out pilot probes backwards, which is totally a thing that could be done. The other thing I could do is I could have XA communicate to XA56 in this case. How many steps back do you have to walk? I could have communicated that. Totally viable thing to do. Instead, what I chose to do is I send a message back saying the capture probe actually succeeded, and for the very first time, actually, back here in the main capture probe test, this MRD test, this test to see whether a message is available, is actually going to succeed. So he's going to actually jump back down to here. At this point, we are actually going to try to receive a message. So this is sort of a handshake between these two saying, all right, XA is acknowledging that XA56 actually got a message. And so it does have to read that message, otherwise we're going to lock up the sending bot. So that's all that is. It's just clearing that queue. But then we're going to go into local mode for message passing. We were in global mode because we had to send messages across boundaries. We're now going to go into local mode for both of them, because what we're going to do is we're only going to send a message between these two when both of them arrive back here. When this guy gets back to here, if this guy is already here and is trying to send a message, then it will act as a sentinel for this guy. So I'm using the sentinel logic because I'm going to put XA in a position where it can be a sentinel. Now, for that to work, the mode has to be local messages only, or at least it may not have to be. You may be able to send global message anyway, and that might have still worked. But I wanted to play around with this command anyway, and I didn't want a message sent from a different node to make it through. So that's a good debug check for me, right? Okay, so it's going into local mode. So the only message that'll work is the one where XA is already here and has already tried to send a message. And XA56, the bot that did the capture, has worked its way back and has gotten to this tail end, and it can test every step along the way. It is a message pending, and it's the only kind of test without death that I can do. So this is a great way to do this. So I'm going to set the mode, and this guy, the XA56, which is on the capture probe return loop, has to do a whole bunch of delays as it walks back. But at the end of each delay, it's going to do a link -1, which will take a step. It'll then test to see whether or not there's a message pending. And if it doesn't find one, it just goes back to the top of the loop. Why all these no-ops? Because the other bot is not only walking back step by step, but it's also popping all of the values that it has in that file out. It's popping values off the stack and only following the ones that are -1, which means that by the time you get to the end, the file's going to be empty because the stack's empty. I did not have to do this. There are lots of different ways I could go. I could have counted up the -1s again and just made that many steps back and then thrown away the file. Maybe I could have had this guy use a pilot fish and then just have this guy use this guy as a sentinel. There's all sorts of ways that I could have arranged XA to get all the way back to the top. I chose a way that sort of mimicked the mechanism of putting parameters on the stack. And in this case, I wanted to unwind the stack as I went. And what the implication of that is as I walk back, I'm again testing to see whether or not I see a -2, which means I'm totally done, or I see a -1 in case I want to walk back up a step, or I see anything else, in which case I just want to get rid of the value. All right, and in fact, I get rid of the value right up front, because what I do is I seek back one in order to be able to read it. I copy it out from the file which does the read, and then I can safely pop a value from the file without affecting X. So in any case, it's popped the value early. I don't have to do it later on. I popped the value out of the file early, and the only existence of that value is currently in X. But that's enough, because at this point it says, is it -2? No, I'm not ending. Is it -1? No, I'm not popping up to the top. Or actually, rather it is, I'm not moving, but I am popping back up to the top, but the value's already been erased from the stack, so that's fine. Then I'm going to seek -1, which basically goes back a value to be able to grab the next value on the stack, right? So this is basically walking back, not you, it's walking back you. Now in this case, at this point, all of the remainder of the values are -1s. So what I should end up with is, when it is -1, I don't just go back to the top of the loop, having erased the value. I follow the link, but then I go back to the top of the loop. So the value's already been erased, but in that special case, I fall through and do a hop back a step. And so at this point, it's going to go down all of those links until it's back at the top. But you can see that XA is always in advance of it. And that's why... XA is always in advance of XA56, but that's why this one has all these knobs, because I have to give XA a chance to go through all of its logic, and in the worst case scenario, XA always stays ahead of XA56, because they're not talking to each other. The only reason this works is because of timing. So XA has to take its time making its hops, because it's doing all this unwinding of the stack to get to the root. But XA56 just waits around and follows the links back blindly. I could have had XA follow links back blindly as long as it knew where to stop. It doesn't know where to stop. XA56 knows where to stop because of the Sentinel. So at this point, the main program literally sees the -2, jumps to main end, and it tries to send a message to somebody in his local cluster, which he cannot do, so he stalls. XA56 happily finishes off the no-ops, walks back up, goes back up to the top of the loop, does a bunch of no-ops, falls back up. Now, this time when it tests the MRD, there's a message waiting. And at this point, we do not pass back up to the top. In this case, we send a message back to XA. Sorry, we receive the message being sent from XA so that XA can continue its program. And XA56 doesn't get stuck here because it's receiving a value, which it then ignores because it doesn't really care about the value, just that it's done this handshake. So XA is done, and you can actually see that up here. XA is simply going to hit the halt. So XA is done, it's going away. XA56, on the other hand, is dropping a file, but then it is also done, and our test run is complete. So this is a proper in-order traversal with the caveat that it has to use pilot drones, pilot X's, to do tests in the future that might cause the bot to die. Because the only way to query whether or not something will succeed is in that message passing. There are no other instructions that I'm aware of that enable that. Nevertheless, that's complete. Now, the reasoning behind this, it's kind of unfortunate that this was set in the last spot as the default case, because it suggests maybe the code only works when it gets all the way through this thing and the stack is sort of maximally stretched out or whatever. That's not true. If one of the next example, incidentally, is in the middle, and if we get to the middle and we find the file, then the same logic works, and we back our way out of here, and we end up chewing up all of the extra directions we wanted to go, because as we do that return to start, we just throw away any work that does not take us to the root. That's to get XA to the front. As far as the probe that actually picks up the file, the EXA that picks up the file, it just follows back until it finds the sentinel. So that logic still works. In fact, if we hit play and follow this, it'll do exactly what it did before, doing all those tests for the death of the pilot bots, till it grabs the file and walks its way back. I find this hypnotic. I mean, there's lots of animations out there of in-order traversals, and they're totally cool. But there's something really neat about seeing these bots do it, given the constraints of the assembly language. I find this just delightful to watch. It's going to try to search down that path. It's going to walk back, search down here, grab it, and then the two of them are going to walk back, and they're done. But it's going to do this each and every time. I'll do one more watching this by hand, and then I'll just hit the fast forward. Now, I will remark, this program is way too long. It's about twice as long, a little bit less than twice as long as is allowed to solve this problem. So this is not what they intended me to do. But I wanted to do it this way, just to prove that there was a mechanism by which to do it. I really wasn't in any doubt. It was more like, can I find that way to do it within a reasonable amount of time? This is such a silly way to do this. The answer that they expected clearly was learn how to use the clone facility, not just for pilot fish, like I'm using here, but for literally the walkers as well. And don't bother with any complicated logic that involves keeping track of your previous state to be able to walk the tree. I just did this because I felt like it. So, as you can see, solves all the cases. But, the size of your solution exceeds the size limit for this task. Your scores are not eligible for histograms or leaderboards. Okay, so, that's fantastic. And I thought of a bunch of different variants, but at some point you just gotta return to desktop. We're gonna play the outro. Would you say that you had friends? Are we friends? What, like you and me? Did you forget I'm making you hack things in order to earn doses of your life-saving medication? True, but you are also providing me the only opportunity I might have, so work and payment, I guess? I mean, there is the ethics problem. Would you call that friendship? Business friendship, maybe. Either way, this is good data for me. Okay. And we're about to go on to a new puzzle. But I have to go collect food. So, we are going to take a brief moment to step away from this. I don't think I can do an overlay of a... let me see. Can I do a notepad? Will be back soon. Collecting... I'm not actually going to say what I... Okay, so I'm not going to say what I'm doing. Please be patient. What I really should do is come up with a canonical graphic for this that I can then overlay, but let me just do this just in case anybody pops back. So, we're going to do a window capture, do a notepad. Okay. Where is my notepad window? There it is. The doink. How clever is that? Not very clever at all. But in any case, I will be back momentarily after I collect food. It's going to be a few minutes. Call it... I'm not going to try to set anything more complicated than that. If I do, I'm going to break something. So I shall be back. All right, ladies and gentlemen, we are back. I suppose I should probably throw my headphones on. Not that I strictly need it for this game, but, where are we here? There we go. I think I've got it. So, I have a little bit of sushi in front of me, or off to the side of me anyway. I guess I can get rid of that. Let's just do a double check on the stream to make sure that the audio is still working. Wouldn't it be embarrassing if it hadn't been on all this time? Yeah, okay, audio is still working fine. Perfect. Absolutely fantastic. Right. I'm going to go with the noodles first. I got myself some lovely udon. I'm going to eat at you on the stream because I don't do this for a living. I'm just doing this because I enjoy doing it. But I also need to feed myself. And it's either this or shut down the stream. Nevertheless, I'll try not to slurp that loudly. So that... Oh, that's the broth for what is ultimately my noodle dish. That'll work. Except I am going to need, there we go, chopsticks. Because why would you do anything else? All right. Right, so we are in a position where we're going to try to tackle the puzzles. And so, so exploring the phone system, I look there. Let's go to UC Berkeley. We're going to say connect to the network. Here we go. There's another file I want to grab. All right, so this is going to be another explore a network kind of thing. And I'm not going to do a bonkers implementation like I just showed you with the recursion. I mean, unless I have to keep state. I'm going to try to do it sort of the exploit the swarminess where appropriate. Oh, delightful noodles. So, let's think about this for a minute. What are we going to do here? There's a file I want to grab. They tried to wipe everything clean, but luckily there's a set of backups. Always keep a backup, right? What happened? Oh, nothing in particular, just normal research project stuff. Alright, so our AI friend here, and it's clear, spoilers, it's clear that our friend is an AI, because I think they told us at one point. As if they needed that to tell us that. Wants us to nick something that was part of a research project. Okay, so locate a specified host, either tape 1, tape 2, or tape 3, and then locate a specified entry, which we can't read. At least I can't read that. I'm not even going to pretend. There's a tape backup file that in that host. File 200. Create a file in your host containing the entry's data. The names of the target host and entry are available in file 300. For more information, see accessing data in legacy storage systems. So I was having enormous trouble, if you recall, trying to actually solve the previous puzzle, mostly because I didn't recognize that it was a bot that was holding the file. Once I figured that out, but I've already actually read through all of the legacy stuff. Now I'm going to have to go back and refer to that in order to get the right syntax for manipulating it. But I already read all that out. So if you want to see that section in the document, go back to my previous video. So, I am definitely slurping. All right. Create a specified file in your host and leave no trace. Okay. So, I have to go to one of 3 different locations and try to find the relevant entry and then copy the data out. Now, I'm not going to try to... How am I going to do this? It's more or less symmetric in that, although one of them is more distant than the other two are basically the same distance. So I don't really think I'll have one walker go in there and start cloning itself as it goes left and right. This is not really going to save me anything. I think what I'm going to do is I'm going to spawn 3 bots to do the work. Actually, I could start up 3 individual bots with 3 individual programs. Now that I come to think of it, because it's a fixed number, I don't have to clone it and walk down it. By the way, for the previous puzzle, I probably could have done that. I could have probably created exactly the right number of bots that had specific rules. For getting to the deepest part of the thing. All right. All right, kind of a little bit simple, I guess. The thing that they're trying to teach you is the interaction with the database protocol, not really the moving around or searching. All right. So we're gonna have 3 bots. And it's too bad they can't share common code, because actually I suppose they could. I could get clever. If I send out 3 bots, I'm going to be able to open up the relevant database and look for data in it without actually having the bot explode, I think. So I could do this in parallel. If I did it sequentially, then I have to basically have one bot go in there, try to find it, and if it fails, instead of dying, it would then go to the next sections and do more work. The thing is, I'm going to want the same code to do the searching in each of the 3 cases. So the question is, so I think a tape backup system involves going to the end of the file, searching backwards through the sort of database. Yeah, so I can see some of these here, right? Searching backwards through the database to try to find a name. Then extracting the relevant sections of the file, or the section of the file that has the data in it. And then copy that data out. So I gotta make sure that none of the ways in which this can fail. I'm gonna make the assumption, and this may be unwarranted, but I'm gonna assume that there is at least one piece of data in each file. And the reason I want to assume that, not only one piece of data that has one file that has backup data in it. The reason I want to assume that is because if I try to do a seek, if I try to do a seek that goes too far back, it's just going to hit a wall, because you're allowed to say seek minus 9,999 in order to go to the beginning, for example. Which means seeking negative 50 when there's not enough space isn't going to crash the bot. What that means I'm going to have to search backwards through this file to try to find out to see if I have a match. But I'm also going to get into a situation where if I try to search backward, I don't know how many entries there are. So if I go back far enough, I'm going to end up with a number instead of a label. I want to have have the bot stop doing its work and if I have 3 bots, I want the bot to basically know when it can basically kill itself. But unfortunately, like reading a value. Oh. So I need a test that tests to see whether or not a value is a label. And amongst the things I can do a quality test and it won't crash. So I could deduce whether or not it's a number or not by whether it fails all possible comparisons. That's one thing I could do. And that'll do it without exploding the bot. I could grooving out to the music here. Very serene. I could instead try to do math on a label or on a value. And if it turns out that the math doesn't explode, then it's a number. And if it does explode, it's a label. I think, because I don't think you can do an add I or something on a label. Problem with that, it's actually the opposite kind of thing that I want. I actually want it to die in the other case where I try to look for a label, but it's actually a number, and I don't think there's a label-specific test. I don't know if I can deduce where I am in the file. The only thing I can do is force myself to one end or the other of the file and count. I could count up the number of entries in a file, and then I could use the size information. That's complicated. I think I have to use, if I want to walk back and stop trying to process the file early, like I basically walk back 3 elements from the end, find an entry. Walk back 3 elements from the end, find an entry. When I get back to this one, if I walk back 3 elements, I'm going to find a number. By entry, I meant name. I'll find a named value. I'll find a number, but I want to be able to test to see whether or not it is a number. Because if it is, it's not part of the trio. Because then it could stop and go off and do other things instead of heading home. So if I send one bot out to visit each of these things, find the relevant spot in the file if it exists. If it doesn't, I want to head on to the next one, and then the next one, and then stop. Then the question is, how do I get the information back? Now, the logical conclusion would be either carrying the file back, if my wanderer does it, or send it back by way of a communications protocol. lower cycle count if I do all of them in parallel. But possibly duplicated code. And unto you, I say. Alright. Well. Soup consumed rather messily and publicly. Let's try to figure out. I think what I'm going to do is I might do this by way of having 3 separate bots do the work. And if one of them finds it, they send a message back to XA and the rest of them just die. And if that file is only in one location, I'm going to make the assumption that the relevant entry is only in one of these and not in more than one. The wording doesn't really super clearly say that, but... Oh, wait a minute. So, names of the target host and entry are available in file 300. So, I don't even have to search before I know which entry it's in. So, okay. Okay, so... XA is going to stay home. And it's actually going to copy memory to file. So we have to create a file in your host containing entries data. So we're going to make okay, you're going to have to think about this too. Okay, grab 300. Copy from the file into memory, into sort of transmission, the transmission thing. Copy the relevant file name. No. What we're going to do is we're going to, first of all, we're going to have an acknowledgement thing here. We're going to send out to each of the 3 bots we're about to make. Of course, we're going to have these already explicitly made, so we don't have to spawn them. Just because it's easier in this case. They're all going to be doing slightly different movement behaviors. Send it out to each one of them basically globally, saying where they're supposed to go. At which point, one of them will actually find out that they're there, and the others won't. The ones that don't will die. The one that does is going to send a message back. So we're going to copy from M into X, but we're just going to ignore it. Because we don't really care who's sending the value, just that somebody does. At which point, we're then going to copy F to M to send the next piece of information, which is the file to locate. And at that point, we're going to go into the mark file read loop. Transmission copy loop, file copy loop. All right. At this point, what we're going to do, we're actually going to drop the file that we have. We're going to make a new file, and then we are going to have a loop whereby we copy. We're going to actually test. We can't test. Can we test? We need a way to test for end of file. So we're going to transmit the data. Okay. What we're going to have to do is we're going to have to get a file size, because we can't test end of file. We actually could test end of file if our timing is right. Not end of file. We can test to see. Actually, that's another test, by the way, that we can do. We can test to see whether or not we've reached the end of file without crashing the program. So it's not quite true that there's nothing other than message passing that has an end test like that. But we don't have the ability to necessarily send a unique value which acts as a sentinel, like a null terminator or something. We have no idea what's in the data. So we either have to do it based on file length, or we have to do it based on synchronization. I don't really feel like sending along a copy of the value. I'm going to do it by way of synchronization, which may use up more cycles in one sense, but I'm going to try to make that work. I'm going to try to make that work. I have wasabi. Alright, let's write a little bit more code before I start digging into more food. So what we're going to do is we're going to test to see whether or not we have a value available. If there is, from that source, we're going to copy from M into F. And then, we're going to false jump to done, or end copy loop. And then we're going to branch, which is just a jump, to file copy loop, and then mark end copy loop halt. And actually, we don't even need to have a halt, so that'll save us a line of code if nothing else. Right. Now for everyone else, they're all going to be very, very simple. So XB is going to basically link 800. And notice, by the way, that some of these are non-backwards traversable links. So we couldn't have gotten a bot in here and then all the way back out anyway. So the intent here is, in fact, isn't that interesting? You could actually walk all the way around because you can go around in a cycle. So you don't have to have a trapped bot, but I'm going to use 3 bots anyway. So link 800. So actually what we're going to do is we're going to have everyone copy M into X. This is the label that we're trying to get to. So link 800, we're going to test. So actually we're going to copy this into T, because in a moment we're not going to need it. We're then going to test, so we're going to host X. We're going to test, X equals T, and we are going to jump end if it's true. If it's false. False jump to end. Then we're going to have down here mark end. Then here we are going to have what happens if we succeed, which is going to be the file copy loop. Right. And to make this work, so let's figure this out here. We are going to first of all say we've succeeded, so we're going to basically copy F to... Oh, does the global copy send to everybody? This is something that I don't actually know. Oh, we're going to find out, aren't we? Because if it doesn't, it's going to be really, really short. So actually what we're going to do is we're going to see whether or not... We'll just do this bit. Link 800, link 801, link 800. No, it's not 801. It's like link 800, link 800. So this is gonna go link 800, 1, 2. What's in 243? Nothing? Am I missing something? I'm going to have to check the PDF on tape storage systems. Each sheet contains 0 or more backups. I think the 234 is a red herring. For our purposes. I'm not entirely sure what that is. Another file? Because the names of the entries we want are in file 300. Okay, so this is not going to be... Okay, so we have to go link 800 here. So 800 to get in, 2, and then 3 to get to the first one. So this is probably going to take more instructions than I strictly wanted, but... So you are going to have to go 3, 4, 5, so... And then you are going to have to go 7. This is where I'm going to have more instructions than I strictly need, right? Because one of the things I could do is I could have I could step into that first room, and then I could have a go to next room operation that that just takes 2 steps, and then I could incrementally go to each one as is relevant. What the heck? Let's do this in parallel just because it's a way to do this. Huzzah. All right. So actually, so let's say XB. So this one here does not contain the relevant value in question. So it's just going to die. All right. Let's figure this out. So we need to copy a message back saying that they acknowledge that they got a message, so that they basically unlock XA. Because at this point we want to go into synchronized behavior. So that is going to match up with this guy here. Now we want to receive the entry that we want to find. Right. So this is going to be the find operation. You know what? Let's start here and at least see if we're part way into being able to do this. So check that out. With the global send in question, we are only going to get it out to one target, and it's not even clear which one goes. And that was probably in the specification for the instructions, so I probably should have been able to identify this. But let's just go and check it out. So, communication. Okay. We need to go to copy. Copy the values of the first operand to the second operand. The M register controls an X's message passing functionality. When an EXA writer writes the M register, it will be stored in the X's outgoing message slot until another single EXA reads it. If an EXA writes the M register, it will pause execution until the value is read. If an EXA reads from the M register, it will pause execution until a variable is available to be read. If 2 or more X's attempt to read from another X at the same time or vice versa, one will succeed, but which one succeeds will be unpredictable. Interesting. By default, an X can communicate with any other X in the same network. Okay, so it is still just a single pass. It is a single X to X pass, 1-to-1. But that doesn't matter, because what I can actually do, let's just reset that. I can just send this first value out 3 times. So we can't copy F to M, because then it'll be gone from M. So we copy F to X, and then we copy X to M 3 times. Because that will get it out to the 3 bots that are listening. And it doesn't really matter which order they go in, right? So let's try this again. See, and now all 3 of them are going, but each one of them is going to end up in a different location. And there we go. At the tail end of this, all of them are in their respective locations. Really did not provide me a lot of soy sauce. Oh, I'm gonna go get a little bit more because I have a little bit stored up in my fridge. Oh, plenty of wasabi, not a lot of soy. Not getting that. Tuneless humming, because if I try to hum along with it, I will make a complete hash of it. All right. So we have a thing here. We have a thing that starts up correctly. The only thing that's really going to happen that's different is the tail end of this. And if I really wanted to try to make this more compact, I would try to find a way to code share. That is, I would basically have the startup operations of these differ, but at the point at which they succeed or fail. Point at which these things succeed or fail, they would then either die or go through these looping operations. And I'm sure I'm going to be over budget on instructions, or at least at the high end of the number of instructions, by doing it this way with the explicit 3 bots. Because the tail end of this loop is actually going to be completely common. Which is a bit unfortunate. That is a spicy bit of sushi. All right. You know, the more I look at this, the more I look at this, the more I want to do this in one bot. So the end copy loop is just going to halt. I'm going to have basically mark start. So I got to go at least start 1, 2, 3. Start 2, 3. Start 3. We're gonna also have a mark. So there's gonna be we're gonna actually nerf all of this in a second. So hang on. Start 3. Mark start 5. And mark start 7. And then gonna have a go down here. Mark go. All right, let's see if we can trim this up a little bit. So all of them are going to need differing amounts. All of them are going to need at least one step just to get into the maze. right? So we're going to have that here. We're basically going to have a start, we're going to have a link 800. But that means that this can have a link 800, right? Which is going to be 2 more than this one. It's going to be 2, which is going to be 2 more than that one. So we have different ways of starting. We're going to have to jump over. There's going to have to start up in a different way each time. So we're going to do a mark start copier. So start searcher, start search. We're going to get a message saying which version of this we are. So we're going to say mark start search. We're going to say copy from M into X, and X is, this is basically going to actually copy to T because we're going to throw this away in a minute. What we're going to do is we're going to start each of these up differently. Instead of doing it this way, what we're going to do is we're going to actually grab 300. We're going to, not even going to do that. We're going to, before that, we're going to do copy 3 into X. Sorry, 3 into M. Copy 5 into M. Copy 7 into M. That's going to start up each of the 3 items. Each one of them is going to go through a different amount of work, and hopefully, based without having to have a complicated communications protocol, we can then send we can then do the sending of the 3 the startup values to each one of them. And what that means is that once we do the starting, okay, so we have to be careful here. So test T is if T is equal to 3, because it's one of our tests, then true jump to go. This logic is going to be the same here. I can't use double equals, that's right. It's equal to 5, then jump to go. And if it's 7, so you're testing as 3, testing as 5. If it's 7, we just fall through because this is the only other value it can be. Now at this point, we would then universally go and execute this code. At which point, we don't need this or this or this. So we're only going to do, we are going to have 4 bots, but we're going to do only 1 bit of source code. Because I'm not sure we necessarily saved anything in all of this, because although we no longer have a lot of copies of the link code, we do have additional tests and jump instructions. Nevertheless, we are going to cut down because of all of the logic in doing the searching, because all of them are going to do common operations and only one of them is going to respond. Now, we're going to have each one of them. Each one of them is going to do, we don't need this. We are, however, going to have to copy out the value. Each one of them is going to get a copy of that first value. And we're going to test to see whether or not we're here. And all of those that, where it's, all of them where it fails to be true are going to end up at end. But one of them is going to pass through and is going to get into this section here. I'm just going to test this so far to, except I've got red lines somewhere. Yep. So. Oh, and I can't get past that because it hasn't replicated the relevant. Okay, then. What we're going to have to do is, and this is the thing I don't have to do. I'm not sure if I'm saving anything by doing this now and doing this in one program, because I am starting to seriously get into the realm of so there's got a lot of extra code in order to set these guys up. Although, so on the one hand, we start them up generically and pass a value into them to make the determination. By doing this and then testing. On the other hand, we could start up in different sections. That's what we're going to do. We're actually going to get rid of this. We're going to start search 3, 5, and 7. And actually, we're going to do the 7 first and the 5 later. Because it doesn't really matter the order logically, but this will get them executing roughly closer together in time, which may be of use, I don't know. But here's what we're going to do. We don't need this anymore because we're not actually receiving that value. But start 3 can actually be down here. Should have done this in the first place. Start 3 goes there and does 3 of them. Start 5 goes here. And start 7 goes here. See, that's way less stupid. Because the act of doing the different starting locations executes a different number of these link operations, which is exactly what I wanted, and I don't have to do any numeric tests at all. In fact, I don't have to copy values in any way. So the very first things that we actually copy over is the one that gets received here. Yeah, all right. So, one of them should get to this operation down here. I think it's in the last one in this case, but let's take a look. So the one that's already closer to the end is this one here, which is XA2, which is the one that only went 3 spots because it's further along in its code. It jumps to the end and it's out of instructions, so it's taken itself out. And that one's taken itself out, and now we've only got the one that's attached to the actual file. It's relevant. Perfect. I'm liking this. Yay for parallel bot distribution, or what? Okay. So now we actually have to do the sending of the file operations, and this is where we have to synchronize with the other side. So what I want to do is I want to make sure both of them are ready and waiting. So one of them gets to the right location, which is we copy 0 to M, which unlocks it, and then basically we have a mark copy loop. And what we're going to do is copy MX, FX. And then we're literally going to jump to copy loop. Now here's the thing. When we try to copy this value, but there's no data there, it's actually going to crash, which is exactly what we want anyway. We don't have to drop files or do anything. We just want the bot to vanish. So that actually forms our copy loop, and that's as fast as possible. It should only be, so it's not F to X, it's copy F to M. So now it's going to have to wait until we get a reception, and then it's going to have to do one more instruction after that in order to go back to the top of the loop. So that's more or less as fast as that's going to go. Now, the other side of this, boy, this is actually way slower than I thought it was going to be. The other side of this is where we do a copy. So we do a test the MRD to see if there's a message. If there isn't, we go to the end copy loop. We then copy a value out. And then we jump back to the top. So you're actually executing more instructions in order to be able to, so it's going to jump to the top and immediately do a test. So the thing that we have to be careful of is that we don't test when the other one hasn't had a chance to try to write. So at most, we're going to have to delay some of this, like put in a no-op before the MRD, in order to let the bot that is doing the copy get to the point where it's trying to put a message in. So let's walk through this again. We're going to watch this one because this one should be able to get past. Yeah, so we're not actually doing the right search. So that's kind of the problem. We got to search from the right location in the file. Right now it's going to copy the whole file. Actually, we haven't grabbed the file yet either. So we start the search for 7 whatever, and then we basically where is it here? Test jump to the end. So we're copying 0 to M, saying we succeeded. Only one of them is going to do that. Then we have to grab 200. And we're actually going to copy the whole database. We're not actually going to do the search yet because I just want to make sure that this read-write loop is working. Because once we find the right locations and start doing this, it's going to look kind of similar, except that it is going to have to test to see whether or not, instead of testing EOF or something, we're not going to be able to crash out explicitly. We're going to have to count down a counter. As annoying as that is. Okay. So we've grabbed the file. And now we're going to copy in fact the entire thing. So and we are stuck trying to copy from file into memory, but that's the wrong half, right? We actually want to copy memory into file, and that's why that's failing. So this is, yeah, some of these copies are just synchronization operations. And in fact, we don't need this sync operation. And correspondingly, we don't need this sync operation because the very act of starting to send data is going to be our acknowledgement. And we know one of them is going to do it, so. So where are we here? This should be true. It is. We're then going to not jump. We're going to copy to the file. We're then going to come to the top of the loop, and we're going to hopefully still be 1. Yes, we are. So we're going to keep doing that until we have to end the copy loop. So we should be able to Alt, select halt, and we do get to the end. And the other bot, incidentally, has crashed because it got to the end of the file just like I expected, and then we halt. But the problem is we didn't get the specified file, we got everything. And I would argue we did leave no trace, because neither of our bots are alive. But we didn't satisfy getting the file. So the reason, okay, so we're not going to be able to do this trick we're not going to be able to do this trick where we just copy until we die. What we're going to have to do is something more sophisticated. So we grab the file. We then want to search file loop. Now we know that the file is in this place. We know we're guaranteed to find it. So that's something that's helpful. So mark search file loop. So what we're going to do is we're going to do this. We're going to how do I want to do this? Right, seek. So sorry, grab it, seek 9999. Seek. So we're at the end. We then go, no matter how big it is or short it is, we get to the end. We go back 2 elements, so that's -2. Three actually, -3. We then copy F to T. We then test to see whether T. So having done that, though, I'm going to I'm going to put this first seek outside. I'm going to tell you why. Because the first seek that we're going to do is to seek -3. The first seek is going to be a -3, but if we fail, we're going to want to seek -4. Because we're going to want to go back over the one we just read plus another 3. And by arranging it this way, I think we... I'm not sure if we get that much of a trade-off in instructions, but probably none, actually. But let's do it this way anyway. So we copy the value, we test T, is equal to X, because X should still hold the host. No, it's not the host that we want. It's the... So at some point, we're getting copies of all of this, and we actually pull that value. So if we're past this point, we know that the host is the name as the sent file, but then we have to get another value, don't we? Because this is basically, this triple is sending out that first value. We actually have not sent this second value out, so we're going to go copy. The first one that ever does a read after it receives this first value, and make sure that there's no possible way I can end up with a bot getting a message early that it shouldn't be getting. So we're going to copy F into M directly because we don't need to be told when to start. We don't need that back communication ever at this point, because the first point at which that's relevant is inside here, actually. So we send each of the 3 bots the first piece. That's all they need to get to their locations and possibly fail. One of them will succeed, and that's the only one who should read that next value, which is the label value. And at that point, we drop that file, we make the new one, and we start going to the copy loop, and we just copy. So somebody's going to start sending us data. Okay, so at the tail end here, what we're doing here is we're starting up at different locations. We get to the location. We then pull out the host. We test against the host, but then we no longer need the host. At this point, we can actually do copy M to X, and X, the register, is going to hold on to our name that we're going to test against. And so we then grab the file, seek to the end, seek back 3. We copy from the file, the label in the file, into T, and if it equals X, if it does not equal X, we want to keep looping. If it does equal X, we want to start doing the copy thing. So So what we're going to do is we're going to do if it's true, test jump to. We're going to want to copy out the start and the size, and we don't have enough registers to realistically do this, right? Because we had 2 values that we had to pull out. At this point, we no longer need the name. We might just have enough registers to do this. We're gonna have to have a mark copy start. Copy start. But we're actually going to want to. So if we find the right one, we go to copy start. Now we're still attached to the file in question, and we'll sort that out in a minute. What we really want to do here, though, is we want to say at this point we want to seek -4, which will go back over the one we just read, and then back another 3, and then we want to go to jump to search file loop. Now that will eventually end because we know 2 things. We know we're in the right sector. And we know that the entry is in the file name because the wording of this suggests that, and I'm going to operate under that assumption. So if that's the case, then that's going to keep going until it finds the right item. At which point the file pointer will be left one step beyond the label because we just read it and we didn't back up because we jumped out early. If that's true, then what we can do is copy the file to X. We'll copy the file to T, and then copy the file to X. And T is going to contain the start, and X is going to contain the number. Given this, we can now basically do seek -9999 to go back to the beginning. Then seek T, at which point T is no longer important, so we can use it for truth values. We're not going to lose anything. Now what we have to do is go into a copy loop. And we're going to have to do a copy loop until we run out of data. Now I'm going to make another assumption, like until the counter gets to 0. And I'm going to make another assumption is at least 1 byte in each file. Because otherwise, why have it as a backup entry? Now, I could fail on that, but I'm going to find that out eventually. So what we're going to do is we're going to have copied. We're then going to say sub I x1x. We're then going to test x is equal to 0. That means there is 0 left. And jump. False jump back up to copy loop. Is that what I want to do? What have I done here? No, yeah, so this obviously goes away. So we copy F to N because we're at the right location now. And this is going to keep reading forward as X keeps counting down. All right, that's going to be close. Now, the thing that's going to fail us here is if while we're copying, this loop up here doesn't manages to get to the testing before it actually goes and does another copy. So we got the same number of instructions, 4 instructions. So let's see if the timing happens to work out. So we're going to go check out this here. So. All right, so starting the seek, we have backed up to the label in question, which is actually the one that we want. But looking where we're currently stalled here, we are currently stalled. See, here's the problem. We've stalled. We don't know how long it's going to take us to find the entries, and we are already going to go to end copy loop and just stop. And this is why we need that synchronization. So what we need is, after this, we're going to want to copy M to T. It really doesn't matter because we're just going to do a test. All that is a synchronization operation. we're going to say that we're good once we've found the relevant information. So it's at this point where we're going to send a copy of 0 into memory. And that's going to unlock our partner. And at that point, and actually we're not even going to do it there, we're going to do it at the top of the loop. We're going to do it here. Actually, no, we want to get into the position of reading. We're going to unlock it the minute when we know, because no, we're not, because we want it basically to, we want the testing to happen essentially after this has occurred. Now this may mean that this is where we require putting that pause in order to make this loop operate. But let's start with this now. Let's actually get into our corresponding code here. So we're at copy start. So we found the right spot. We're going to seek to the beginning. We're going to seek to the right location. We are then going to send a synchronization message up to our partner. So the copy has put a copy in the buffer, but it can't move until it's read. And the read was stalled on that, waiting for it to be ready, and now it can read. And so when I do again, they both step forward. But now we're in a situation where I think we're going to be one step too late, because this should put a byte in the buffer and the MRD should be tested, but I think they're going to be tested in the wrong order. No, they're not. Because the execution of this happened before the testing. I'm a little surprised by that, I'm not going to lie. But basically we read, we're going to read 8916. And up here, we're going to copy that into the file, which is 4976. Now, why did that occur? Oh, because it was the one done back here. Now, where did that copy occur? Don't know. Gonna start that again. Oh, because... All right. That's to the beginning. We get to 4976, and then we copy 0 into M. We then copy F into M, so that's going to advance once, while at the same time we're testing the MRD. So the read out hasn't occurred, but the file's been advanced. Like, it's been read out of the file, but it hasn't been sent yet because that requires actually doing this copy. Now we're going to do the test. It's not the end of the loop. We're going to copy the value out. It was already waiting for us, so it can advance. And then this other one is basically at the point where it's going to subtract 1. Right, it's going to subtract 1, it's going to test, it's going to jump and copy. So subtract 1, you see now, and then here's the problem, we're already at the test. So that indicates what we need is, having just done this copy operation, we need at least a few no-ops. I think at least 2 to compensate the 2 instructions, but I'm not 100% sure, so let's just get ourselves down into here. So that's gotten that guy up to the jump to the copy loop. And so then we do a step. Now you're about to copy, and you're about to do the test MRD. Now this should be 1 again, which it is. And again, now what is X actually at down here? It's actually at 16. Oh my god. Oh my god, I think we did it. How freaking wild is that? I accidentally hit play when I didn't intend to because I wanted to watch it all the way through, but let's check this out. Let's hit play. Goes through the loop until it copies out a bunch of values and then hits halt. And it's copying it from whatever file actually gets. It's doing it from any of these three because I didn't test that bit, but it does match logically, right? All right, so let's see if we can get all the way through. Oh, one of them stalled. It's on test run 8. Okay. So why did test run 8 fail? Okay, so we have to test run 8 specifically. So test run 8. The file that's correct is this one. So that one's the only one that should survive. Okay, so where are we in the relevant sections? This one has not yet found the relevant entry. XA is still alive. Where are you? You're still waiting on sending out the individual messages to each. Why are you stalled? Oh, because each one of you is... a couple of you are stuck waiting at go and go. Alright. But the one that got there first... the one that got there first should have been waiting on this one in order to get... this one grabbed it early. See, that was what I was worried about. Is that of these 3 startup values, I think one of these guys went to the wrong bot. It went to a bot that was saying, I am ready, in fact, to do my work. But then how did it send a message back? Hang on, I gotta check this. So each one of them is going to get into this section to test their host. Then they're immediately going to pull out another value because they are the one who succeeded. But I think... Alright, no, maybe not. XA1 is out of instructions. XA2 is out of instructions. We are attempting to write out a byte. But have we gotten somehow past the synchronization byte? No, hang on. The problem is XA0, who is trying to go the furthest along, had to do a couple of extra instructions, and I think we got the wrong value sent to XA2. Because XA2 is already... is searching. In the file, but it's searching for tape 1. because it got this value out of order. Because I'm copying these three values, and then I'm saying to the one that survives, do this work, do this copy. But I think that this one is getting sent to the one that actually first getting sent to XA2 erroneously. Or is getting sent to... Sorry, this one here is getting sent to XA2 as if it were the file name, because it got there and succeeded too quickly. So what I need to do is I need to basically I could delay. What I basically want to make sure of is that I get to the point of sending out each of these three, and none of them can get to the point of doing this read before all of them have gotten the chance to get to that read. So what I want to do is I want to delay this by at least one operation, if not more. Because then that copy goes out a little bit later. Right. So you're the only one who survived. And now we are properly starting to copy the file data across. Yeah, okay, so let me do that again just to show you what's going on here. So it's actually it's XA0 that's going to be the problem, right? So XA0 is actually walking through its movement operations. And each one of them is trying to get a copy of the tape value. But we want to make sure that we don't get to this copy before all of the other bots have managed to get past this. And if I had not had that no-op in there, I think that it would have gotten it would have gone out of order because, oh no, it's not actually A0, it's A2. So let me try that again. I want to start. So it's A2. So let's go take a look at A2. So A2. So if this were one instruction earlier, it would be receiving that value at random sometimes, because there are probably two bots actually listening on a copy XM, right? It's this guy here. XA0 is not getting that message. It's random. So if those two copy MT, this copy MT operation, and was linked up with this copy MX operation, one of them would succeed at random, which means that this would be very difficult to debug. I need it to go to XA0 because it actually has to legitimately test to see whether or not the tape variable matches the host that it's in. So what I have to do is, because XA2 has already decided it's the correct one, it's already barreling forward. And the next thing that it's going to try to receive, or wants to receive, is the actual file name, the specified entry name, not the host name. So this no-op ensures, because of the exact timing of this, that copy out here specifically ends up going to XA0 in the rare case that XA2, I guess the 1/3 case, in the 1/3 case that XA2 is the correct one. Because if XA2 is in the correct one, if this tape 1 unit is the correct one, then we're going to get here just a little bit too quickly. So we do a no-op instead, but that means that this guy is waiting around for the next write out, which is just in the process of happening. Now at this point, that means that this guy recognizes he's no longer there, no longer needed, and this guy recognizes he's no longer needed, so neither one of them is relevant, but this one continues on its merry way. Now when that no-op is in the other position, it's going to delay the others, but they're not going to matter. That delay isn't going to matter, because the copy-outs will have already gotten all the way to this one, waiting for whoever's going to get there to... Yeah, okay. And actually, this works out that I actually sent the guy for the distant one on a little bit early, because if I sent him out late, he would get there late. This guy would even... but if this guy was successful, this guy would be even farther advanced in his instruction set. So... yeah. My getting these guys all into position to start doing their work as early as they can in the global cycle pool was a nice happy accident. Because they all end up roughly reading these values at the same time. If I'd done them in the other order, these values would be far more stretched out in their reads, and I might end up with a bot that succeeded accidentally claiming one of them. All right, here we go. And we're good. So, some crazy people getting down to 38 instructions. More power to you. I'd love to know how you did that. My execution time, my cycles, is actually higher than it should be. Well, what are you going to do? Yeah. I could think about this to try to figure out, if you will. Try to figure out who managed to get, or how they managed to get a tighter cycle count. I suppose... yeah, I don't know. I'm doing a lot of synchronization. So if I only had one other bot out there, it wouldn't matter. I wonder if the cycle count... if you have more than one bot executing in a single step, whether or not that counts as one cycle or n, because that would make a difference. I would hope that if you spawn more bots, you use as many cycles as a step times the number of bots. Maybe I'm wrong. Wow, 38 instructions. Way less synchronization, I'm guessing. You could have had a loop that iterated over... you could... Ooh. Here's an interesting thing. You could have a bot that from the first... so you could basically start in that first room. Let's think this out. I may not implement this. I'm not sure. I kind of want to go on to like other puzzles. And this actually, the stream is getting on, and I've had lousy sleep, so I may go and just read a book or something. So continue editing. So let's think this out. Let's say that you just arbitrarily started a bot in here, like the startup, like you had one guy that was roaming around this doing the work. Yeah, that's interesting, isn't it? You could actually, you wouldn't have to have a copy. So I did copying of the file by way of message passing, but there is a cycle here, and you can actually get back home. I might take another stab at this tomorrow, actually. I don't think I'll do it tonight. I need sleep, and I need to do actual work tomorrow. But so let's think this out. Starting from this thing with the 243 in it. a loop could contain the following operations. Move 2 steps ahead, open the file. See if you find the right element in there. If it's not, if it is, then you could basically move forward until you got to here. You'd probably have to have a sentinel bot in here, so that you could test arrival. But that's plausible, so you could basically go local messaging only, right? Because from here, step in, search this. If you find it, then just keep stepping forward until you get to here, and then go in here and drop the file off. Right? You could actually do that with XA alone. You wouldn't actually... except you'd have to have a sentinel bot in here. So, fine. Have a single sentinel bot that basically steps in here with its mode in local and writes out a message, just like we use the sentinel bot in the tree, right? And that would be a couple of instructions, and it would just sit there... it would essentially sit there forever, but I guess you would also want to clean it up, so you'd have to have a shutdown mechanism. That's all right. You'd write out a message, receive a message, and halt. And then anybody who needed to use it as a sentinel would get there, read a message if it could, test to see if it can read a message, knowing that it's there, read the message, write out a message to shut it down, and then the sentinel bot could die and the other bot could go into here. The loop itself would be simple enough because it would be step, read, see if you can find, if it does, find the sentinel. But if it doesn't, step, read. If it finds it, then it goes for the sentinel. It's going to be in one of these three, so that eventually it is in fact going to find one, and then it's just going to search for the sentinel and then leave. So a version of this could involve all the same start logic, but the setup wouldn't involve all of this bot copying. Ah, crap. You know what? I may have to actually, so copy that. So, right. Let's add the Exa. Let's add the Sentinel. So this is going to link 800. It's going to copy copy 0 to M. So it's going to try to write out an element. The person who finds it is going to try to send an element, so we're going to go copy MX, and then we're basically just going to let it die. That's literally all that guy has to do ever. Right. So we're not going to do any of this spawning nonsense. We're not going to do this copy loop in this sense. We are going to, what are we going to do? We're going to want to copy out to a separate file. Oh. No. Because the problem is you can only hold on to one file at a time. So it actually helps to have one reading and one writing. But instead of having all the copies of the bots and then have all this complicated logic as to where to go, XB, so mark end copy loop, jump to end copy loop. So we are going to work this out so that we do this. We're going to do, instead of doing this, I'm going to do that. So the Sentinel is going to be the guy that's actually going to be storing the file, and then after it does the end copy loop, it's going to basically link 800 and drop. And actually, to start with, it's going to, once it gets in there, it's going to make a new file. Make a new file, go into the standard copy loop. Then move out and drop. the minute that it's out of data. Okay. Do you have any of this junk in here? Not in that sense. So we're not doing any REPLs. Okay, we are gonna have the. Okay, so we're actually have the Sentinel do a little bit of upfront work here. We're not gonna link first. We're going to grab it because the Sentinel can grab the file in order to relay the information. But when it gets its message, it's going to drop. It's going to. All right. Making a bit of a hash of this, but we're going to copy that out and we're going to send it out to its buddy. So first thing it's going to want it's going to grab 300. It's going to send out these two values. The minute it can send out this value and get past that line, and actually we don't even need to do this. So we're going to grab f of x. We're going to copy f to m, the first value out to the only drone that we have. We're then going to copy f of m out again, which is going to be the second value the walker needs when it needs it. But when it does that, it's going to be in a position where it has to wait until it finds the value. So you're going to want to copy a value back in. We don't actually need it to be a Sentinel. It can just be here. So we don't have to link anything, we can just drop. Because what we're going to do is once we find it, we're just going to destroy ourselves. Like once we find it, copy the data, we're just going to destroy ourselves. So all of this bit is once we know where we're going, or once we. So okay, mark start search. Brain is starting to short circuit. Okay, let's bail on this. What we're gonna do, first thing this guy's gonna do is link 800. That's gonna take it into the start of the first section. It's going to take one of the guys into here. That's our walker. XA is our walker. It's going to go to here. From that point on, every 2 legal steps is takes us to a valid spot. So we don't need any of this. We do know that at this point we're in a valid spot. We copy out the and we're going to make sure that we link 800, we're going to copy this out. So that's going to get the host that we're looking for. That's the host. Well, that's the one we're looking for. Start search takes 2 steps. We then test to see whether or not we host into T. We'll host into T. We'll test to see whether or not X is equal to T. And if it's false, we actually go back up to start search. So that entire loop right there does searching of the first host that actually matters, and one of them is guaranteed to have the value. So we don't have to worry about it accidentally dying here and not being able to communicate ever again. After that occurs, then we're basically at the point at which we're going to prep to do the searching of the file. So we could, just for giggles, we could say mark search file. We're not actually going to jump here, but we then need to know that second value from the guy that stays behind. We grab 200. seek 999, so all the rest of this logic is actually the same. Alright, let's see if this even steps right. So this guy goes here. We're then waiting for that first value. Now this copy is going to stall until we need it. So we don't care about that, but now we're going 2 steps. We're going to figure out if the host matches. If it does, if it doesn't, then we jump to start searching it. Oh, it doesn't, right. So the host is tape 1. We're actually after host 3, aren't we? So now we no longer need X. We copy M into X, which gives us the actual file name. Grab 200, seek, and now I think we're going to have a problem where we have, we're going to copy, we're going to see if it's the right one. If it is, we jump to copy start. Copy a value. So now we're looking at the copy loop issue, and the copy loop issue is we need to get the start and end values. Hang on, I have goofed something up here. So copy loop is going to, so we pull out the tape and pull out the name. And we send that across. And now it's all timing based. Okay, so let's do that again. So we copied out the relevant name, and now it's going to go into a search, and we found it. Now we are currently waiting on, we're copying 0 into M, so we're waiting to send out a message to synchronize, because we don't want to test this early. So in order to have this work, see now at this point we're going to copy T and, oh, hang on, yeah, so copy, that's okay, copy T into X, F into T and F into X. We seek, we copy 0 into M, and that sets off the synchronization. Oh, that's not right. We are trying to wait. So I want to copy M into X because we want to wait on that write before this goes, because then we're going to be in our copy loop. And I'm going to take that make, and I'm going to throw it here because why not? So let's try this again. Why did that fail? Cannot grab a second file. That's why I don't do that. Because I'm an idiot. So we have to actually do a drop make copy MX. Now that copy M into X is just used as a synchronization mechanism. So let's try this again. Okay, we copy over the relevant entry, step back, verify that it's correct. This is the synchronization mechanism, which should get both of them to advance. Now we got copy with test. It passes. I want to do a couple of steps so that we jump back and our test is lined up with the copy. Then Our test run is complete. And you can see that this is working no matter which one actually starts it out. So let's give that a run. We still have 169 lines. No, 169 cycles. We are not trimming it down. Now, possible solutions here are to do what's called... so I've got 47 instructions. I don't know how they mesh. That is crazy. That is crazy. I could see using fewer cycles by unrolling the loop for the copies, because for the big copies, you know, in order to do that counter loop, you have to execute a subtraction, a test against 0, and a jump. And then you have to do the copy itself. So to do one copy, you essentially have to do 4 instructions. Whereas if you unroll the loop and say did batches of 4 at a time, you could then do 4 copies and then only 3 additional instructions. So 7 instructions to make 4 copies. But then you might have some left over at the end, and then you have to do a little chunk to do that tail end. And so you'd probably, on longer copies, get a net benefit in terms of the number of execution cycles, because you spend more time doing the copies. But that would actually increase the instructions, because you would have to add a few extra steps at the tail end. So there's an interesting question. In those leaderboards, is Broach's double entry there on the same solution or on different solutions? I don't know. That's mental. That's really amazing that they're able to get it down that low. I'm definitely not fighting that this evening. I already went way above and beyond the Call of Duty to do what I did here. I've been doing this for 2 hours and 47 minutes. So this is where I'm going to call it. I would love to know what their solution is, to be perfectly honest. Yeah. Yeah, I don't know. Slight rearrangements of the code might be able to get rid of an occasional jump, because it happens to fall through just to an end. Wow. Stealing back 9 instructions to get the size down. And I might save cycles by doing it, because I'm only out, but except look at that, I'm out by 21 instructions just to get down to Monster Hunters. There's no way I can get down to Broaches. How can you do that in 128 I guess if you don't have the loops at all, because you know there's only 3 elements, so why do it in a loop? Except that would increase the instruction count. The cycle count. The instruction count, the length. The size. Wow. Yeah, I don't know. That's pretty amazing. could you... I don't know how you would copy from one file to another fast. Without using a second bot. I did not save any instructions by doing it this other way. I think primarily because the looping mechanism to iterate over each of the sections didn't save me enough compared to the fact that the different entry points on my bots were really only, like, say 2 instructions different. Like, I didn't save much doing it that way. Wow. I'm not an assembler programmer. People who think in assembly at this low level, as a matter of practice, I'm sure could find all sorts of neat ways to work this out. Like, I've got a true jump to copy start here. What if I rearrange this, for example? So that I only did one jump. Like, I didn't do the extra instruction, and that search is in the middle of something, right? So I could reorganize this so that because if I had test to see whether or not I'd found it, I could do something like this. Test to see whether or not, no. I could say test to see whether or not, because this would only work for certain kinds of files, but if I did true jump, instead if I did false jump, do this, T false, no, false jump, search file loop. I took out this, and then I did seek 3 here, then basically I'd be backing up 4 each time, but I'd back up too far that last step. And then I would have to re-advance. Now the problem is as long as the seek -4 didn't go off the beginning of the file, that's probably still equivalent. I don't know, maybe. Nope, it failed. Because see, then I would advance. Oh, I would have to seek 4 because I'd actually, okay, so that's why that failed. So if I seek 4, does that get me through? Actually, it does. Right? By doing it this way, I trim down the cycles because I'm doing fewer operations in the loop. And I'm able to get away with that only because that seek doesn't fail. Which could if I were really close to the beginning of the file. But in this data set, that doesn't occur. So I can cheat and get away with that. So in the copy loop, once I get the copy started, there's only one jump to keep the thing going. So that's not a problem. But in this side, in order to do the copy, we test the MRD. And then we jump out to the end of the loop if it fails. But what I could do is... So that's the synchronization operation. What I could do is move this up to above here. And here, so that the false jump ended up going to, so true jump, if there's stuff to do, then go to File, Copy Loop. I don't need to do this jump. And what happens if I just die? Do I drop the file? I think I just drop the file in place, so actually I technically don't need that. Oh gods. Okay. Okay. Oops, I don't need to do that either, so... Don't need that. And the question is, do I need these operations? So the thing is this is kind of terrible because I'm not doing the MRD test. And I'm not doing an early bail. So this will only work if there are actually... That might work. So this is going to copy out at least one byte every time, which may be valid because we wouldn't be because there wouldn't be an entry if there were no data. Maybe, like, it depends on whether or not zero-length files are allowed. So let's give this a shot. It's out of instructions because... Okay. So we are going to run until we get to here. Now we're here, and now we're starting to copy values. So we copy a value. We gotta line this up. But we're out an extra instruction here, so we need to add an extra no-op here, which is technically, see, wasted instructions from that point of view on this side. So yeah. That's actually fine so far. If we run that, saved 2 cycles, only 2 cycles, but we got down an extra couple of instructions. All right, so there are things we can get away with because we make assumptions that happen to be true but aren't specified in the spec. One of those in this case is copy out is copy an extra value. So the advantage to this is we literally are copying out we have to do the counter in either case, right? That's interesting. We have to do the counter on either side. If we did the counter on the receiving side, then it wouldn't have to do the no ops. But then the copy would be sending values. It wouldn't know when to halt. But we could have it halt by testing a return condition that says please stop copying. Damn. That's how we might be able to get away with this. We have to do testing anyway. So on the what we could do is we could have the copy loop on the transmission side. Instead of doing the countdown copy with a subtraction, it would actually do a simpler test. It would just test the MRD, and if the MRD didn't receive a value, or if the MRD didn't have a writable quantity saying that it was done, then it would keep trying to send values, but then if it got blocked trying to send, it wouldn't be able to check that anymore. The biggest problem is we don't want to do a read or a write unless we know there's going to be an exchange. I don't want both of them necessarily running counters. Life cycle stuff. We could so clearly if a bot is killed, it drops the file. So we could do, instead of doing testing of the MRD, we could quite literally just keep copying. But then we have to have a way for the source to kill the destination. But I bet you there's a way to do that, because if we go yeah, I don't think there's a way to do that. I was going to say we could kill either the transmitter or the receiver artificially if it gets into a locked up state. It wouldn't matter which one, because even if it were the receiver, they would drop the file that they're building, and that would just be the end of that. And if it were complete, then you'd be done. But we're not in the same location, so we have to negotiate that. And it's not clear to me, looking at instructions, that there's in fact any way wow. Brain getting melty. All right, nope, that's it. That's it. Brain is starting to get melty. I'm trying to argue my way in circles. So basically, I've got two different possibilities here, and I managed to trim down the loops, the key loops, a little bit tighter. But I could increase the number of instructions and unroll loops to get a lower cycle count. Or I could. I don't think I can get it any tighter in terms of a reuse of instructions. I mean, I probably can. There's probably a way to do it. They clearly have some really clever coding in order to be able to reduce the instruction count at this point, but it is not clear to me. The only thing I can think of is that that it's counting white space as code. So if I were to just run this to completion, and it says size is 45, and then I go back in here and I get rid of all of my white space. Yeah, currently 45, so that's fine. It doesn't actually count white space, and that's good, and nor links for that matter. Oops. Guess I gotta have that extra no-op in there, right? I might be able to do with fewer copies and receives if I were a bit smarter about how I walked around in the world. Like I could have it so that XA, who's doing the wandering, grabs the relevant host first, drops the file, and then could we, if we took the file with us, actually, maybe we could destroy it when we're in there because it's our file. It's just an input thing. We could grab it, take it with us, possibly even use it as scratch space if we cared to. Maybe that's it. Because if we were to say grab 300 and then instead of doing a drop we did a wipe, that's not actually going to change the output of the code, is it? No. So there's an interesting thing. We don't need to preserve the file. So we could actually have A grab the file and take it with us. And then when it finds the right location, pulls out the name of the file, the name of the entry it needs, without ever having to do any of this communication at all. You'd still want the agent, I think, back at home base ready to receive, but then that's all it does. Son of a... I'm gonna hate myself. Not what I wanted to do. Delete that. We want to actually copy this. Thank you. This is going to synchronize the minute the first byte gets sent, so we're actually going to do that. And that's literally all it's going to do. It's just going to sit there and act as a repository. This guy is going to grab 300 first. It's going to link, it's going to step, and actually it's going to, instead of copy M to X, it's not going to do any of that. It's going to copy F to X. It's going to do the link. It's going to do this search mechanism, which is not going to modify X, but only T. We're not... Okay, so in here, we're going to copy F to X again, because we're searching for an entry. We're then going to do all the search file loop stuff until we find the right location. We copy the relevant bytes. We don't worry about the synchronization. And we just start the copy loop. Oh, except that when we get to the point where we're grabbing the 200, what we want to do is we want to wipe the file that we're in. Because we've already pulled out the relevant value from it right here, but then we don't need it anymore, and then we can grab the 200. So, alright. Get to the right spot, that's fine. Wipe it, we don't have it anymore, but we don't need it because we have the relevant file name. Grab 200, we do all this logic, and then when we get to the bottom here, we're now doing the synchronized stepping thing. Oh, except that I did something terribly silly there somehow. Yeah, that's fine, but we're closer. So we're going to get to... And we're waiting for a value from here. So copy F to T. Seek forward. Pull out the relevant value, seek to the beginning, seek to the right start location. We're going to copy F to M. But XB has no file held. Okay, no, that's fine. Because what that means is that what we really want to do in XB is make. And we are going to get to here. Actually, no, we're going to get to here. Okay, by the time we get to the MRD, we're doing another copy. My length is down to 41 instructions. Now my cycles are still high. But the instruction count's gone way down. Maybe I could find another 2 instructions. I'm less worried about that. I have no idea at all how anybody managed to get down to 128 cycles. That's mental. I can only hope that somehow those entries do not correspond to the low size entries. Like, these are separate wins on separate solutions. See, I'm okay on the size amount now. I don't really feel like trimming that. I'm just not sure what I would do to trim the cycles without increasing the size. So I'll call that... see, I don't want to get obsessed with the leaderboard because then I could spend way too long on this, and I just want to see more puzzles. I want a variety of puzzles. I don't want to harp on this because that's more fun for you guys anyway. But take a look at that, right? So I'm at 3 hours and 13 minutes, and I'm going to call this good. Return to the desktop. Kind of a shame what happened here. There was some interesting research going on. What do you have to do with this place? This network? Just a place where I used to hang out, that's all. Okay. Hey, Gast, can I submit an article? Yeah, anyone is welcome to submit. Very cool. Just has to be good. Learned about geographic information systems the other day. Sounds interesting. Fair enough. All right. Yeah. So that'll be an exciting thing to check out tomorrow. Or a couple of days from now, because I really do have to get sleep and I really do have to get actual work done. So it's been delightful. This is Code Weaver. I have been playing this really fun program game, Exapunks, and I will completely continue doing this. All I can say is that if I do any of the coding off stream, because I may just need a break and this might be a fun thing for me to do, I will then show you what the results are after the fact, as well as the story beats that come along with it. But that may not happen, because there's a good chance that I will be here at my terminal to do this, and if I do, then I will live code it with you right here. Thanks so much for stopping by. This is Code Weaver Plays Games. I will see you in the next stream. Thanks so much for joining me.